The next section is about taking one of these regions in the XY plane and spinning it around an axis to create a solid. When I think of this, when I think of volumes of a solid of revolution, I actually think of wood turning on a lathe. So here's a video of wood turning. We're maybe not going to watch the whole thing, but when he's done, he has a fairly complicated looking shape. One way you could find the volume of the shape is you could dunk it in water and look at the displacement. But another thing you could do is you could slice it into very skinny discs, and each disc would be a cylinder because this thing spun around. And you could calculate the volume of each of those discs and add up all of those volumes. That's the calculus way. The other way is more of a physics way. All right, so here's a visualization of solid of revolution, just another one. So you have a region in the plane. You take a rectangular area and you spin it around an axis. And so each of those little rectangles spins to make a cylinder. And if you can calculate the volume of all of the cylinders, you can add up all of those cylinder volumes and get the total volume of your region, of your shape. But it's even better if you can calculate using infinitely many of these rectangles. So here's a region. It's enclosed by f of x equals 2 plus x cosine x and the x-axis from -2 to 2. And we're going to revolve this region around the x-axis. So we're going to take that region and spin it around this x-axis. So in other words, we could take a rectangle and use it to sweep out a disk around the x-axis. And if we did that infinitely many times, so each of our rectangles sweeps out a disk or a coin, then eventually we'd wind up with kind of a vase shape, and we'd have all of these disks that we get when we spin those rectangles around. Okay, I'm going to take a look at just one of these disks. So it has a little tiny thickness that's going to be like the height of our cylinder, the little tiny thickness. Because we sliced it perpendicular to the x-axis, that little tiny thickness is going to be dx. And then it's also going to have a radius. The radius is going to be the distance from the x-axis up to the curve. So in other words, the radius is going to be the y-coordinate. But since we have a dx, we don't want to use the letter y. We'd rather use the definition for y. So the radius would be 2 plus x cosine of x. Sometimes the radius would be smaller, like when we're at -1 here, the radius would be pretty small. And sometimes it'd be bigger, like if we're at x equals 1, our radius would be bigger. But this curve will determine that for us. Wherever we are on the x-axis will determine how big our radius is. So the volume of just one of these, because it's a cylinder, would be pi r squared times the height. And now if I want to use the magical adding tool to add up all of these infinitely many, infinitely skinny disks, I'm going to take an integral from -2 to 2 of this volume. So this is very similar to what we did in the last section, except that in this section, all of your cross sections will be circles. You won't have any triangles or squares. You'll always have circles because we're always going to be spinning, and that's going to create that circular shape. We are not going to solve this integral. I'm going to leave it right there. We could grab a calculator and solve it, but right now we're just going to work on setting up the integrals because we've already worked on solving integrals before. All right. For this example, we are going to take the region in the first quadrant enclosed between the y-axis, the x-axis, and f of x equals cosine inverse of x. We are going to spin this solid around the y-axis this time. We're going to spin this region around the y-axis. So I hope you can kind of picture that you're going to get kind of a, I don't know, like a shape of a temple roof maybe out of that. And if I draw just one of my discs, the thickness of my disc this time, because we're spinning around the y-axis and we sliced perpendicular to the y-axis, the thickness of my coin is going to be dy. The radius is going to be the distance from the x-axis out to the curve, which would be the x-coordinate. So the radius would be x, but we don't want it to be in terms of x. We want it to be in terms of y. So we're going to take a look at our definition of our curve, y equals cosine inverse of x, and we're going to solve that for x. We could take the cosine of both sides. So our radius is going to be cosine of y. When we spin around the y-axis, our slices are going to be perpendicular to the y-axis. We're going to have a dy, and so our radius needs to be in terms of y. So in order to calculate the volume, we're going to calculate from y coordinates. So we're going to go from y equals 0 until this point right here. What is that point right there? Well, that point is when x is equal to 0. So when 0 is cosine of y, oh, that would be pi over 2. So we're going to go from 0 to pi over 2 of pi times cosine of y squared dy. I'm going to stop there because I know you could type that onto your calculator. All right. Third example, this time we're not going to spin around the x-axis or the y-axis. We're going to spin around the line y equals 1. So we've got the function 3 sine of x minus 2, and we're spinning it around y equals 1. So now I think we can imagine we're spinning around this line. So like here where we'd have this distance would be 3. So we'd have a distance of 3 here. So it would kind of look like a funnel shape maybe. Okay. So this time our slices are perpendicular to the x-axis. So the little tiny thickness is going to be dx. And this time our slices are not the y-coordinate. Our slices are, the y-coordinate is down here, right? So our radius is going to be 1 minus the y-coordinate, which would, because the y-coordinate is negative, 1 minus the y-coordinate would be 1 plus the absolute value of the y-coordinate. So this is going to be our radius, but because we have a dx, we don't want it to have a y in it, so we're going to have 1 minus 3 sine of x minus 2, which would be negative 1. No, it would be 3 plus, sorry. It would be 3 minus 3 sine of x. And so then our volume of one of these things would be pi times the radius squared times the little tiny thickness. And the volume of all of the little things, all of them put together, would be from x equals 0 until we get to this point, which is when 3 sine of x minus 2 is equal to 1, or when sine of x is equal to 1, so that would be pi over 2. Oops. So we're going to integrate from 0 to pi over 2, and we're going to integrate pi times 3 minus 3 sine of x squared dx. And that would give us the volume of that shape. All right. Last example, this time we're going to take the region that is under the natural log of x, but in the first quadrant for x is less than 4. And we're going to revolve that around the line x equals 4. So we're taking this shaded region, because it's in the first quadrant and it's under natural log of x, and we're going to spin it around this line here. This line is like the x-axis, so when we spin around this line, we're going to get disks with a tiny thickness of dy. And so that tiny thickness of dy is going to tell us that we would like our radius to be in terms of y. So our radius is going to be the distance from 4 to this curve. So the radius is going to be 4 minus the x coordinate. But we don't want it to be in terms of x, we want it to be in terms of y. So we're going to take a look at our function and exponentiate both sides. Whoa! And so we get e to the y is equal to x. So our radius is going to be 4 minus e to the y. We're going to integrate from, now we need some x coordinates, y coordinates. We're going to integrate from 0 to natural log of 4. Because this point right here is the point where x equals 4 crosses natural log of x, so that would be 4 comma natural log of 4. And so we're going to integrate pi times the radius squared. Oops, not just e to the y, it's 4 minus e to the y for this one. All right, so some quick summary things. If you're spinning around a vertical line, like the y-axis or any other vertical line, then you're going to have a dy. You're going to have a little tiny thickness that's a change in y. And that means that all of your equations need to have y's in them, so you're going to need to solve for x. If you're spinning around a line that is horizontal, like the x-axis, then you will have a dx in your integral, so you'll have to make sure you solve your equations so that they have x's in them. And then if you're spinning around a line that's not an axis, you have to pay attention to how you would subtract. For this one, we would do 4 minus the x-coordinate, because the x-coordinate would be the distance from here to here. So we want to do 4 minus the x-coordinate. So pay attention to which order you would subtract in. Sometimes you would do x minus 4. So it kind of depends on which region you're subtracting around which line. The good news, I will never ask you to revolve around a line that is not vertical or horizontal. So you never have to worry about solving, like revolving one of these regions around like y equals x, because that would be crazy. All right, that's all I got. Thank you so much. Bye.